Hello, everyone. This is the second lecture for the Big Data in Earth Science module 2. In this lecture, I will continue talking about the bias-variance trade-off. So in this lecture, you will learn the bias-variance trade-off, a fundamental concept in machine learning. So the mean square error of an unseen, the test point, is a result of two competing forces, the bias and variance, and the inherent noise in the problem itself. This will involve examining the theoretical properties of an estimator. Here we set the data generation function, which we already saw before. And let's go to the deep note script and where we can find this code. So when you check this second deep note script under the M2 folder, you can find this function here, the same function. And previously, we generate the x value from the uniform distribution, which randomly extract the x value from 0 to 1. And this is the true function, the fx. And we have the y value, which include the random error from the normal distribution, 0 mean, and standard deviation. So previously, we explored only one realization from this function in the last class. And realization here means that we have access to only a portion of the underlying data as our training data. So this realization can be underrepresentative of underlying population or representatives. For example, if we poll only houses where a household has certain education level, or if it is done without racial, educational, age, or other types of biases, we're gonna have very bad training data. For example, previously we fitted several polynomial regression models with the same training data. So just imagine that if the training data is biased, the fitted model can be biased a lot. Now, suppose we drew another training set, the data set, using the same distribution and the sample size and 100, then we would get another fitted curve using the new training data, like the blue and orange line here. Get this here. While the two curves are visually similar, they are not identical. If you look more training samples, we would get more fitted curves. So what we wanted to study in this section is the likelihood that we will happen to get a good fit given a single training data set. So if we drew another set of training data and fit the model, we're gonna have another line. And if we drew 50 training data sets, we're gonna have 50 curves, just looks like this. So the statistical properties, before I move, let me show you how I generate these two curves from the deep note. Here. So we have 100 sample and the degree of freedom, the degree for the polynomial model is 4. And I made the training set, the training data set, the two-dimensional train n by two-dimensional training data set. And I also created the empty matrix, the array for predicted values to save. So here I learned two times of these models to get two curves. So please take some time to understand this code line. So the statistical properties of an estimator can help us understand its potential performance. Let D training is our training data, and let theta hat is the theta hat which is the estimated parameter calculated from the training data. So if we put 50 here, we're going to have 50 data sets. And for example, the theta here is the true parameter, I mean the true value from the true function, and theta hat is the value from the estimated function. And theta hat is also a random variable, which means it has a distribution. Now let's consider the distribution of theta hat, f hat polynomial distribution. This is a distribution of the fit at x equal 0.05 to 5 from a polynomial of degree 4 using different training sets. And I generated 50 different training data sets, each with 100 samples, and fit a polynomial model to each data set and recorded the estimated at x equal 0.05. So when you check the deep note, you can see how I generate the figure. So NOS here is the number of simulation, and here is the number of sample. So I simulated 50 times of this model and predict the value at when x is 0.25 and recorded this predicted value here and make the density distribution using the SNS, the KD plot function. Please take time to understand this code. So next, the formula that connects the test mean square error to bias, variance, and irreducible error is this equation. The first expectation here in term, this one, is over the distribution of unseen points x. So all these three terms on the right-hand side are non-negative, and irreducible error is not affected by model choice. This means that test MSA cannot go below the variance of random error. I will now derive the formula for given test point x, and since it will hold for a given test points x, it will also hold for any distribution of unseen test points. So equation one here is because y is fx plus epsilon, the random value, and second equation is because of square expansion, linear property of expectation, and independence of random variance and random variable epsilon and f hat. Remember that when two random variables are independent, the expectation of their product is equal to the product of their expectations. And in equation 3, we see how test MSE decomposes to irreducible errors, the error here, and this expectation value. Let's see how this later term can be further analyzed. So in equation 4, we subtract and add by expectation of f hat x, and in equation 5, we expand the term inside the square. And bias of expectation of f hat x minus f x is just a constant value, since we subtract fx from the expectation of f hat x, which is also a constant. Therefore, applying expectation to square the bias, the expectation of f hat x minus fx square does not have any effect. In equation 6, we are able to pull fx minus expectation of f hat x out of the expectation because, as we mentioned, it is just a constant value. Lastly, the equation 7 holds because of linearity of expectation. Therefore, we see in equation 8 that expectation of fx minus f hat x square is the sum of squared bias and variance. When we combine equation 3 here and 3 and 8, we end up with this last equation, the summation of the squared bias, variance, and irreducible error terms. I know this is complex, so if you have any question, please do not hesitate to contact me. I will explain you in more detail if you want. So finally, the expectation expectation, E in the right-hand side is over the distribution of the test data. So once we observe the training data, the resulting estimate may be great or horrible. However, these theoretical properties provide insight into what we can expect and how much confidence we can have in the estimates. Next, we can estimate the model variance and bias with simulation. First, generate new data for simulation of M, the number simulation of M, and fit the models with the data, the DM, to get the F hat from this simulated the training data. And now we can estimate the items of interest with these two equations. So I made 6 figures to help you understanding what I have been saying. So I ran 2,000 simulation to generate the lines. So we have 2,000 lines for each figure. Let's check how I did this in DeepNote. So here, the number of training data is 100, and I made 200 fitted lines for 1, 2, 3, 4, 5, 6 polynomial models. Please take time to understand this code line. So as you can see from this slide, these figures, we have 2,000 lines for each polynomial model, and the fitted models can be very different if we use different training data sets. So the right figure shows the bias and variance of each model. You can see that as the complexity, the degree of the model increases, the bias decreases. But here the variance increases, especially at the edge of at the edges here. And the bias is difference between the two regression function here, the black lines, and the model's mean, which means the bias is model's mean, maybe here, maybe like middle of these 2,000 lines, and difference between the middle of these 2,000 lines and this solid black line. And the variance is seen in the width of transparent curve, one for each simulation. So this width is variation. So notice that model variance and the model bias vary over X. So this x-axis is X. So please check this code line here to understand what I have just said. Furthermore, to help see what is going on, we now look at the distribution at X equal 0.05 and X equal 0.55. As you can see from here, the estimated value for X when X is 0.05 or X is 0.55, the theta hat, which is the predicted value from different polynomial models. As you can see here, they can be very different even if we use the same degree polynomial model. So please look at this code line here to understand what I just said here. So the previous analysis examines the MSE of F over a set of X's. However, in a real setting, the overall test error will be based on all of the actual tests, the X values. So we are usually more interested in the integrated MSE. I calculated MSE in 2 different ways, and they have the same value. Please try to understand this code as well. The main point of this lecture is that we desire to find a predictive model that has just the right complexity. This will depend on both the true complexity of the data as well as the sample size. A model that is too complex will have low bias, but potentially have high variance. And a model that is not complex enough will have high bias, but lower variance. In a real setting, we will only observe one training data, a single curve here, and we'll have to decide the optimal complexity. So here, let me show you the entire distribution of MSE value, one for every simulation. So these figures means that if you have just one training data with polynomial degree 1, you will happen to have the MSE over this range of the value. So you may have the polynomial model with MSE value 7.5, or maybe you will end up with the polynomial model degree 1 with MSE around 10. Yeah, I really hope you understand these two figures, and please contact me if you cannot understand this lecture. This is really important to understand the machine learning concept. And finally, below is the table of the number of simulations that each model had the best MSE. While the degree 4 model does best, but degree 5 or 8 are sometimes best. If we examine more models, we would find the degrees between 3 and 9 would sometimes be the best model. And please take a look in this code line. So now here are 3 main take-home messages from this lecture. First, in our toy example, a polynomial with degree 4 is the best model in principle. However, for some data, some simulations, the models with degree 8 and degree 2 performed better. Second, the above analysis or this analysis is what is meant by the bias-variance trade-off. In reality, we only get to observe one realization of the training data. So we can never actually estimate the bias and variance the way we did here. But we can still estimate the risk, the MSE, by using resampling method like cross-validation. More loosely, when people mention bias-variance trade-off, they are referring to the principle that the best model is one that has just the right complexity. And if the model is too complex, it is unlikely to produce a good estimate across the entire range of inputs, because it is likely to stray far from the expected mean at certain values. On the other hand, if the model is not complex enough, then it will not track with the expected mean across the ranges of the input values, and thus produce poor overall performance. Lastly, performance of a model can vary across the input features, the X. If you are only concerned about performance in a specific range of X, then you may want to emphasize these during the training processes. And if the X values are coming from a different distribution than the training X values, then your model may not be optimal. That's it for the model to lecture video.